Our next speaker is Juliana Pimentel. She's a postdoc at University of São Paulo in San Carlos. And today, Juliana is going to talk about asymptotics of scalar parabolic PDEs with infinite time block.
Thank you. So I should start by saying that I'm very grateful to the organizing committee. I thank especially Professors Diego and Ricardo for this opportunity to talk here about my work. So this talk is going to be about the long-time behavior of a very simple but yet very general class of equations that are defined in one-dimension space. So, and this is based on a work that was done in collaboration with Professor Carlos Rocha from the Universidade de Lisboa. So this is the outline. I will start by presenting you the class of semilinear parabolic equations that we are going to study. And as our main goal here is to consider a non-dissipative version of such equations, I will start by telling you what has been done for the dissipative setting. So after that, we set the non-dissipative context that we are going to work on. And the objective will be to describe the dynamics on the associated non-compact global attractor. Then we present the main result we have obtained in this regard. And we conclude by telling you what were the main tools we have used to prove this result. So here we are interested in this type of equations, scalar reaction diffusion equations of this type, that are defined on some bounded interval, say 0 pi. And here we are assuming that it satisfies some Neumann boundary conditions. It also works for Dirichlet boundary conditions with some minor adjustments. So since we are assuming here that this nonlinearity f is a C2 function, then we have a solution semigroup that is locally defined. And it is locally defined for U0 on some appropriate state space. So, but we can also impose some further conditions on this function f. We can assume, for instance, that this function f is a dissipative function. And what do I mean by that? Is basically that the solution semigroup will be actually globally defined, and every solution will be eventually bounded. This basically means that for every solution, there is a time t that will depend on the initial condition, such that after this time, the solution will enter and remain within a fixed large ball in the phase space. So for this to happen, we can suppose, for instance, that this function f satisfies these two conditions here, a sign condition and a growth condition of this form. So if this is the case, for instance, then we say that this function is dissipative and our problem is going to be dissipative. So the solution semigroup will be globally defined, for instance, in this phase space here, H2, with Neumann boundary conditions. So if we are dealing with a dissipative equation, then we have guaranteed the existence of a global attractor for our semiflow, which is a subset in the phase space X that is defined in this way, is a non-empty compact invariant set attracting every bounded subset of X. So in this case, we have guaranteed this object in our phase space. And there are basically two main results regarding the characterization of this object. The first one says basically the following. If we assume that all the equilibria of our equation is hyperbolic, they are all hyperbolic, this means that lambda equals 0 is not an eigenvalue for the linearized equation at this equilibrium point. So if this is the case, then the global attractor will be given as the union of all the unstable manifolds of each of the equilibrium points. So this is the first characterization for the global attractor in this case. And we also have the following. This other theorem is a consequence of the existence of a Lyapunov functional for this equation. By using that, we can prove that the global attractor in this case will also decompose as the union of the set of all the equilibrium points and the heteroclinic connections between them. This basically means that these heteroclinic connections are the orbits that are globally defined and converges backwards to an equilibrium and forwards to a different equilibrium. So in this case, in this dissipative setting, we have these two main results for the characterization of this global attractor. In both of these cases, we are considering this function f to be a dissipative function. If this is not the case, then we have, generically speaking, we have only two more options. In the first option, this semi-flow that will be induced by this initial value problem will exhibit solutions that blow up in finite time. So if you have solutions blowing up in finite time, we then say that this equation is a fast non-dissipative equation. So not every solution is globally defined. Or our equation has all the solutions defined globally, but at least one solution will blow up in infinite time. So in this case, we say that our equation is a slowly non-dissipative equation. So generically speaking, these are only the two only remaining class of equations for that problem. So this first class here of equations has been studied for quite a long time, and it is still an ongoing topic of research. But the second one, just very few things are known for this second class. And this is precisely the class that we are going to consider here. So the first question is how I can guarantee that my equation will have this type of behavior here. My equation will be a slowly non-dissipative equation. It turns out that the simplest interesting case is that to consider a positive linear growth for our nonlinearity f. So if we say that our function f is of this form here, so b is a strictly positive constant, g is a bounded C2 function, so in this case, we can guarantee that this equation with this nonlinearity will be a slowly non-dissipative equation. So this means that all the solutions will be globally defined, but at least one will blow up in infinite time. And we refer to the solutions that blows up in the solutions that blow up in infinite time. We refer to them as grow-up solutions. So in this case, we are saying that if f is of this form, then this will ensure grow up with no blow up. So the problem that we are going to consider is precisely the following. So our equation is going to be of this form. We have this nonlinearity here. It's defined on this interval 0 pi with normal boundary conditions. We assume b to be strictly positive, g to be a bounded C2 function, but we also have to assume another hypothesis for this function g. We assume that it is globally Lipschitz in the second and third variable. And it's going to be clear later why we have to impose this other condition on this function g. So what I'm saying is that in this case, if we consider this type of nonlinearity, my equation is going to be a slowly non-dissipative equation. And why is that? First, we are saying that our function g is a bounded function. So with this condition, we can prove that the solutions of these problems are all going to be globally defined, for instance, in this phase space x alpha here. So x alpha is going to be the associated fractional power space associated to this sectorial operator here. So for instance, in this phase space, we have globally defined solutions. And we moreover have the following result. If b is a strictly positive constant, then at least one solution of our problem will blow up in infinite time. So with these two properties here, we have exactly the conditions we need for our equation to be slowly non-dissipative. So it is going to be, in fact, a slowly non-dissipative function. So what we have is the following. We have a solution, at least one solution, that is globally defined and blows up in infinite time. So this basically means that this solution will not be eventually bounded. And with this, we lost the compactness for the attractor. So in this case, we don't have a compact global attractor associated to this semi-flow. So the object that we are going to consider is what we call a non-compact global attractor. This non-compact global attractor is defined as the non-empty minimal set, which is positively invariant and attracts all bounded subset. So this object is going to be minimal with respect to these two properties here. So this is how we define this non-compact global attractor. So this object has been considered in this paper by Chepijov and Goritsky in 1992. In this paper, they consider a much more general equation, an evolution equation, and they suppose their nonlinearity is not a dissipative nonlinearity. So in this case, they prove that the non-compact global attractor associated with the equation will still be given as the union of all the unstable manifolds of the equilibrium points. And in 2010, Nitz and Bengal considered a scalar reaction diffusion equation with a nonlinearity that is with a linear growth, a positive linear growth. And she was able to prove a more complete characterization for this global attractor by assuming that this function g only depends on the function u. So what we did is to generalize this result to include the case where this function g also depends on the spatial variable x and the derivative of u. So we were able to prove, to generalize this result, to characterize the dynamics on the associated non-compact global attractor. And we were also able to prove much more simpler criteria to determine the existence or not of heteroclinic connections between two equilibrium points. And we also were able to prove this combinatorial characterization for the global attractor in terms of a permutation that will be related to this problem. So what I'm going to do here is to present you the main result we have obtained regarding the dynamics of the attractor. And we are just going through the main ideas for the proof of this result. But before I can present you the main result we have obtained, I need to introduce the concept of an equilibrium at infinity. So for this problem, we observe the following. This problem is a non-dissipative problem, but we still have a gradient-like structure for it. And this is basically because of the existence of a Lyapunov functional for this equation. And with this property, this gradient-like structure, along with Lassalle's invariance principle, shows us that any bounded solution will actually converge with time to some bounded equilibrium. So every solution that remains bounded will necessarily converge to a bounded equilibrium. So what we have is precisely this result here. If you consider any solution u of our equation, then the solution u will either converge to some bounded equilibrium, or it will be a grow-up solution. So given any solution of our problem, we only have these two options. It will converge to a bounded equilibrium if it is a bounded solution, or it will be a grow-up solution, which is an unbounded solution growing to infinity with time. So we already have the asymptotic behavior of our equation, of a solution, if this solution is bounded. So what we want to do is to describe the behavior of a solution that is unbounded with time. To do that, we have this result here in this direction. So these phi j here are an element of this orthonormal basis in L2 under Neumann boundary conditions. So this result basically says that if U is a grow-up solution, then there exists an integer k that is strictly less than square root of b, such that the normalized solution will converge. It will converge in the L2 norm to plus or minus phi k. Both this sign here and this k depend on the solution U. And here we show how this dependence works. So this k here will be such that this limit is going to be 1. So this element here and this one are the eigenmodes for the solution U when we decompose it in this orthonormal basis here. So k is such that this is satisfied, and here we have a condition to determine the sign here of this function. So what we have is that if U is a grow-up solution, if U is an unbounded solution with time, then if we normalize the solution, it will converge to plus or minus phi k, some eigenfunction of this in this basis, orthonormal basis. So if we consider the original orbit U it will grow up to infinity in the direction of this eigenfunction here. So what we do to determine the exact limit of this grow-up solution U is to consider Poincaré projection of our phase space. And this is basically done in the following way. We take the infinite dimensional space X alpha Cartesian 1, so we identify our phase space X alpha to this space X alpha Cartesian 1, so we basically add one variable, real variable, to this space here, so we consider this X alpha Cartesian R. And then we consider the infinite dimensional upper hemisphere H, defined in this way here. So this is the inner product in the space X alpha. So what we do is to consider the Poincaré projection of this space X alpha Cartesian 1 onto this upper hemisphere here. So when we do that, the infinity of this space X alpha Cartesian 1 will be projected onto the equator of this upper hemisphere. So if you want to study the dynamics of our equation at infinity, we basically want to study our equation projected onto the equator of this upper hemisphere H. And this is basically was done by Juliana Fernandes in 2009. And she was able to prove that by projecting our equation onto the equator of this upper hemisphere H, there is an innumerable set of equilibria on this equator. So what we have is the following. The infinity of our space X alpha is projected onto the equator, and on the equator we have the existence of these equilibrium points here. So this basically motivates the definition of these objects at the infinity of the space X alpha that are defined in this way. The projection of these objects at infinity coincide with these equilibrium points on the equator here. So, and we call these objects at infinity as equilibria at infinity. So this here is basically a more rigorous way of saying that if my grow-up solution converges to phi k, then my original solution U will converge to an object at infinity that is basically the projection of this eigenfunction to infinity norm. So this is basically another way of saying that. So we have this equilibrium points at infinity, and then before we show the main result we have obtained for this non-compact global attractor, we just need two more definitions. The first one is the definition of the zero number of a continuous function. So if we consider a continuous function U defined on this bounded interval 0 pi, then the zero number of U, we denote by Z of U, basically is the number of strict sign changes of this function U. So, and we have this other definition. If U and V are equilibrium points of our equation, they could be bounded equilibrium or equilibrium at infinity, with the zero number of their difference given by some integer j, U of 0 less than V of 0, we then say that these equilibrium points are adjacent if there does not exist any other equilibrium point W, such that these two conditions here are satisfied. So here we observe the following. If both U and V are bounded equilibrium points, all of these properties here make sense. But if either U or V is an equilibrium at infinity, we have to extend this notion of adjacency to include this equilibrium at infinity. And we do that in a consistent way. And what I mean by that is the following. For each of these equilibrium points at infinity here, we have a corresponding eigenfunction for our orthonormal basis. So if we consider this equilibrium point here at infinity, capital phi j, it will correspond to the eigenfunction phi j. So we have this correspondence between these objects at infinity and these eigenfunctions. So this extended notion of adjacency should be consistent with this correspondence between these equilibrium points. So the result we have is precisely the following. The non-compact global attractor, AF, of our non-dissipative equation will be composed by the set of all the equilibrium points, both the bounded and the equilibrium at infinity, and the heteroclinic connections between all of these objects. So here we are basically saying that these grow-up solutions, these unbounded solutions, we are interpreting these grow-up solutions as an heteroclinic connection from a bounded equilibrium to an equilibrium at infinity. And we moreover have the following. If U and V are equilibrium points of our equation, then there exists an orbit connecting these equilibrium points if and only if they are adjacent. So the global attractor will be decomposed in this form, and we also have that the existence of heteroclinic connection between these two equilibrium points will exist if and only if U and V are adjacent equilibrium. So I'm not going to go through all the details of the proof. I've just tried to tell you what were the main ingredients we have used to prove this theorem. So the first thing we observed was the following. We can decompose this non-compact global attractor as the union of two subsets. The first one is, this is a bounded subset, and this is an unbounded one. This ACF is defined as the maximal compact invariant subset contained in some ball B in our phase space. So this is basically to say that all the solutions of our problem that are globally defined and that are bounded are contained in this compact set here. And all the grow-up solutions that are globally defined will be contained in this other unbounded subset here. So if we apply the standard theory for dissipative equations, we are then able to prove that this compact set here will be decomposed as the union of all the bounded equilibrium and the heteroclinic connections between the bounded equilibrium. So we can also prove by applying the theory for these dissipative equations that these bounded solutions, considering two bounded equilibrium, they will be connected by a heteroclinic orbit if and only if they are adjacent. So basically, with this observation here, we solve the problem concerning the bounded equilibrium, concerning the equilibrium that remain bounded. This other subset here, the unbounded subset of this non-compact global attractor, will be an unbounded set that contains all the grow-up solutions that are globally defined, and the set of equilibria at infinity. So what we did was basically to decompose this set here into as the union of these two subsets here. This one is completely characterized by this and the adjacency notion. And now we have just to say how this set here can be decomposed. So this basically means that we want to prove the following lemma. If we take V to be a bounded equilibrium, we suppose that it is hyperbolic. And if we take phi infinity to be an equilibrium at infinity, satisfying this condition here. So this condition here basically means the following. For each object at infinity, we have a corresponding eigenfunction. So if the number of zeros of an eigenfunction is k, so we are taking the eigenfunction phi k. So what this condition is telling us is basically that this equilibrium point at infinity corresponds to the eigenfunction phi k. So if this is the case, if we have these two equilibrium points, then V has a heteroclinic connection to this object at infinity if and only if these two equilibria are k adjacent. So if we want to prove our theorem with this observation here, with some technical details to prove this part here, we just need to prove this lemma. So in order to prove this, we have one direction here that is obvious, not obvious, but it's easier to prove than the other one. So if we assume that V has a heteroclinic connection to this object at infinity, then we want to prove that these are k adjacent. So we suppose by contradiction that these two objects are not k adjacent, and we want to get a contradiction to the existence of these heteroclinic connections here. And to prove that, we basically use this result. This is a result that is due to Angenet and Matano, and it basically says the following. If we have a solution U tilde for, in the space X alpha, a solution of this linear equation here. So here we are assuming that both C and D are continuously differentiable functions, and we assume this satisfies some norm and boundary conditions. Then the zero number of this solution of this linear equation is finite for every positive times t. Also, if we take for some t0 and x0, and this point t0, x0 is a multiple zero, this basically means that this condition here is satisfied. So if this point is a multiple zero, then this condition is satisfied. So this condition here basically means that t0 is a dropping time of the zero number. Since if we take t0 a time before t0, the zero number will be greater than the zero number of the solution for a time t that is greater than t0. So t0 is a dropping time for the zero number here. So what we do is to use this result to obtain a contradiction for this direction of for this proof here. And how we use it is basically just to observe that if we take the difference of a solution u minus v, so if we take a shifted solution u minus v, it will satisfy a linear equation of this form. So this is how we can use this proposition here to get a contradiction and to prove that if there is a heteroclinic connection from a bounded equilibrium to this object at infinity, then they should be actually k adjacent. So we then have to prove the other part, the other direction of this. So we need to prove that if v and phi infinity are k adjacent, then there is a heteroclinic connection connecting these two objects. So to prove that, we basically use two very important tools to get this result. The first one is called a Y-map. This Y-map here is a function that was introduced by Brunovsky and Bernard Fiedler in 1988. And this function is basically a function defined on the unstable manifold of an equilibrium point, taking values in Rn plus 1. And it basically, for each initial condition, it gives all the information on the zero number of the corresponding solution. So they were able to prove that this function here is a surjective function. So this function being surjective basically will provide us with an initial condition u0 in the unstable manifold of this equilibrium that we are considering, such that the corresponding solution u will satisfy these two conditions here. So the zero number of this difference will be given by the k, this integer k, and the sign condition here. So this function, the solution u that is given by this Y-map here, will be the candidate of a heteroclinic connection between these two objects. And what we need to do is basically to prove that this solution u will actually connect these two equilibrium points. So we are assuming that that v and phi infinity, these equilibrium points, are adjacent. So we use that to prove that this solution u will not converge to a bounded equilibrium. So if the solution u will not converge to a bounded equilibrium, this basically means that the solution u will be a grow-up solution. So our candidate of heteroclinic connection to connect this equilibrium are the solution is in fact a grow-up solution. So what we need to do is that this function, to prove that the solution u will actually converge to infinity to this object here that corresponds to this to the integer k and therefore to the eigenfunction phi k. So since the solution is an unbounded solution, we have that result. We recall that this normalized solution here will converge in the L2 norm to plus or minus phi j. So here we notice that this result here is only telling us that this normalized solution will converge to phi j for some j here. But we need to prove that this unbounded solution will actually go to infinity to this object here that corresponds to the equilibrium phi k. So to conclude the proof, we basically need to prove that this j here is actually this integer k over here. So in order to do that, we recur to the theory of inertial manifolds. And this is why we need that condition that this function g should be a Lipschitz continuous function to use the existence of an inertial manifold. So basically, what we need to do is to determine the exact limit of this grow-up solution we are considering. So we need to prove that it will actually converge to this object at infinity corresponding to phi k. So, but since this convergence here is in L2 norm, we cannot guarantee that the zero number of this solution will not drop at infinity. So if the zero number of the shifted solution is k, we cannot guarantee that the zero number of this eigenfunction here will also be given by k. So in order to do that, we will need to work in higher norms than L2. And for that, we recur to the inertial manifold. So what is an inertial manifold? It's a finite dimensional invariant attracting Lipschitz manifold that contains our non-compact lobe attractor. And it is also given as the graph of a C1 bounded function. So what we do is the following. This equivalence, this inertial manifold is a finite dimensional manifold. So we can use the equivalence of the norms in finite dimension. And then we are able to prove that this limit here actually works in the C1 norm. So if we have that this limit here also works in the C1 norm, we then are able to prove that the zero number of this solution, or the shifted one, will not drop at infinity. So with that, we are able to prove that this j here will actually be equal to k. So we then are able to prove that the zero number of the shifted solution is k for every positive time and for t equals to infinity. So this object at infinity will actually be corresponding to this eigenfunction phi k. And with that, we then have proved this lemma here. And then we have, with this lemma, we have conditions for an bounded equilibrium to be connected to an equilibrium at infinity. And with that, we have concluded the proof of this theorem. Just to conclude my talk, I just want to give some comments here. So we are interested in this kind of equations that we call slowly non-dissipative equations. And for that, we have considered a linear growth for our nonlinearity. But there are some more general classes of nonlinearities that also generate this kind of equations. And here I included this condition here that is a more general condition for this function u to satisfy, so that our equation will be a slowly non-dissipative equation. So here this lambda 1 represents the first eigenvalue of our operator. So, and we are also asking this limit to be less than infinity. So this condition here will guarantee that we are not in the superlinear case. So this condition will prevent blow up in finite time. And this condition here is to ensure blow up in infinite time. So if we take a nonlinearity f that satisfies this condition here, it will probably be, our equation will probably be a slowly non-dissipative equation. And our belief is that if we study more general classes of slowly non-dissipative equations, we will be able to consider a larger set of grow-up behaviors and then get a better understanding of this class of equations that we call slowly non-dissipative equations. And with that, I conclude my talk, and thank you very much.